pleasure to meet all of you online. And thanks to that, nowadays the internet is fast. And what I mean is thanks to the bitrate allowance of today's internet. And today I'm talking about a bitrate bound, which is bitrate disallowance on superluminal communication. And first, sorry about this title. And as I can see from the number of participants, this probably already annoyed away a lot of people. Sorry, organizers. And there is more exotic content to follow. All right, first, let me start with a pretty big question, from big question to smaller ones. The big question is, how far can our civilization spread, okay? This is a question that probably only the science fiction novel writers worry about. And if you look at the answers from science fiction novels, there are clearly two classes of answers. And depending on the setup of the problem, either there is a speed of light constraint or there is no speed of light constraint, okay? Clearly, our future in the imagination of science fiction is different. And of course, ever since special relativity, we know that a good physical theory doesn't have faster than light, okay? And there have been growing evidences against the superluminal propagation until yesterday. By until yesterday, I mean, yesterday there was a big focus on positivity bounds, and positivity is also related to constraints on superluminal travel, okay? There are lots of them. And nevertheless, over the past 100 years, there has been many theoretical attempts for faster the light travel. And here, let me organize not in the order of the appearance, the proposals, the time, but order in terms of somehow logical from local to global. First, the most local possibility is a modified kinetic term, the generalized kinetic term, where x is the kinetic term, and you have a function of kinetic term as the Lagrangian. In this case, so if you have the second derivative of this function p to be negative, in this case, the speed for the fluctuation of this field can be faster than light. And of course, we know, and there are a lot of discussions yesterday, that violates some positivity bounds, as I will come back later. And there are some problems. And another discussion that arose yesterday was closed timeline curves and causality. Unfortunately, this type of model doesn't have closed timeline curves. This is because this superluminal faster the light, even if the second derivative of p is negative, that faster the light is associated with a particular background, which is phi dot is non-zero everywhere in this superluminal propagation region. And that non-trivial Lorentz breaking, I mean spontaneously Lorentz breaking background, actually give you a fixed generalized light cone. By generalized, I mean it's wider than the light cone, but it's fixed. It's not related to how the observer boosts. So this will fix the boundary of the light is traveling, the propagation faster than light traveling this direction, but not going to travel backwards in time. So there is no such problem as causality. And this is the most local possibility. And if we move slightly away from local, I mean local flat space field theory, to consider general relativistic effects of bubbles and tubes, there are solutions such as the Alcubierre warp drive solutions, something like this. And these Alcubierre warp drive solutions, mathematically like this and in picture like this, what I show here is the expansion in space, usually the theta in the description of the expansion. The expansion in space is negative in front of the bubble, considering the bubble is moving this way. In front of the bubble, the expansion is negative, means space is contracting in front of the bubble, and the spaceship is here. And the spaceship, although it's not, doesn't have proper motion, doesn't have peculiar motion, is co-moving with the bubble, it will move in space like this and could be faster than light, similar to the apparent apparent faster than light of our expansion of the universe. And to make the space-time regular later, I mean, after the motion of the bubble, you have to make expansion of space to balance the contraction here. And this is the Alcubierre warp drive. And there have been a lot of debates about this possibility. The biggest issue, the biggest concern, in my opinion, is the violation of the dominant energy condition. And why this is a problem is because we are searching for possibilities of faster than light travel, which doesn't appear to be too exotic. And the spaceship doesn't appear to be faster than light. However, you have to have metric. So you have a exotic metric, and you need to have matter to support this metric. And the matter to support this metric, when it violates the dominant energy condition, meaning that the flux of matter is faster than light, which supports the metric. So it's a little bit circular in the argument. And also there is the problem of the closed timeline curve and the causality problems, because the bubble, it is not exactly a local thing, but it's more or less local because the asymptotic space is still have Lorentzian symmetry. And then if we consider the bubble as a point, the conventional argument that if you are faster than light, satisfying special relativity, then you can go back in time, still apply. That if you boost your frame and consider the faster than light motion in the boost frame, that can be considered by another observer as you are moving back in time. So you always have the problems, for example, the so-called grandma paradox, that if anyone travels back in time and then kill his or her ancestors, and then how this person can exist, etc. There are a lot of paradoxes for the closed timeline curves. And there are some solutions. Consider is a problem or not, depending on, I'm not sure it's physics or philosophy or anything. But nevertheless, there could be closed timeline curve. And also there are some horizon problem, etc., that the driver of the spaceship is unable to control the bubble, etc. And there are some solutions slightly better, slightly more under control. For example, the Krasnikov tube, etc., something like this, which still violate some energy conditions as the weak energy condition, etc., and also has the closed timeline curves. And if we move further to other possibilities, more globally, by more global, I mean allow to modify topology of space, then we have wormholes, and probably we are more familiar with wormhole solutions compared to these Alcubierre warp drive and the Krasnikov tubes. So the wormhole solutions recently is also a hot topic because of the discussion of quantum gravity, string theory. There are the possible relation with quantum entanglement. But nevertheless, here, so in classical consideration, there is the metric of the wormhole, and that also violates the weak energy condition. And if we fix the mouth, the opening of the wormhole, that doesn't have closed timeline curves. You just travel in fixed background from one end of the universe to another place in the universe. But if you are allowed to move the opening, the mouth of the wormhole, take it to a rocket, move as you like, then from similar setup as the twin paradox, you are going to, it's possible to travel back in time and create closed timeline curves and possible causality issues. And by the way, so if you are pretty familiar with the wormhole but still haven't read the original reference, so I recommend this pretty interesting read, this original reference. I actually read it yesterday. That's pretty interesting. And if we move further from these wormhole geometries to more global possibilities, there is also the possibility of extra dimensions, which possibly can have faster than light travel. And why it is the case is in extra dimension, there are possible solutions that once you go to the actual dimension, you move in the actual dimension, the space and time scale differently in the actual dimension coordinate, where this h factor dependent on the actual dimension coordinate. In this way, depending on where you are in the actual dimension, the speed of light is different. But still, in a large class of these solutions, I'm not sure if all of these solutions, there is violation of null energy condition. And so there are also some issues. And there are a lot of lots of other possibilities. You can see ranges from almost 100 years ago to until recently. And there is a question that, as you can see from the date, okay, the year of the reference. So that dates back to many decades or almost a century ago. And the question is why I'm starting to be interested in these questions, and why, and also as there are some recent reviews and books, so a lot of other people also get interested in similar topics recently. So why we are interested in this topic? What is a particular time for this study? This is because for all of these possible either space travel or time travel, these solutions, we need exotic matter. And in the past decade, there are a lot of progress in the possibilities of exotic matter, including the discussion of positivity and dominant and weak null energy condition violations, etc. And 20 years ago, we are pretty satisfied with this Lagrangian kinetic term minus potential term for scalar field. And then 20 years ago, people talk about the K inflation, generalized the kinetic term. And then 10 years ago, there is so-called Galileans or G inflation, and then the Hondesky theory, and then the so-called beyond Hondesky or the GLPV theories, and even more beyond the Dost theories, etc. And this is just one example of generalized theories, exotic matter, and modified gravity. And there is a huge catalog. For example, considering the community of modified gravity, there are, for example, the possibility of massive gravity or minimally coupled, minimally modified gravity, or the generalized vector fields, etc. Discussed a lot. And for example, we can refer to Shinji and Lavina and Filippo's wonderful talk on Monday about many of these possibilities. So the last decade, we really has lots of possibilities opening up for the possible discussions on positivity, although this is not so positive, just constraints from positivity. And the dominant energy condition, all the kinds of energy condition violations by fluctuations given a background. And there's a huge literature. So this huge literature enable us to reconsider a lot of problems in different opinions. And in my opinion, so people are, so first of all, still there is no confirmation or not even evidence from experiments that any of this exotic matter exists. However, by a lot of people considering them pretty seriously in the context of inflation and in the context of dark energy, in my opinion, it may make more sense to study such exotic matter in superluminal travel. By more, why do I mean making more sense? By more sense, I mean two things. The one thing is there are all big questions. I mean, inflation, the origin of the universe, dark energy, the fate of the universe, and faster than light travel, what is the limit of civilization? Okay, all big questions. And the fate of the civilization, the limit of civilization is probably more crucially related to the this exotic matter. So probably it make more sense to apply this exotic matter study to superluminal travel. And also superluminal travel might be more useful. I mean, just in case it exists after all, just in case there are these exotic matters, so it may be useful. I mean, we don't value the theoretical physics as is being useful or not, but it doesn't hurt to be useful as a nice addition. So this is the motivation. That's why I am interested in looking into this field at this particular time. And also to summarize our motivation in one sentence, that the rise of the superluminal topic is because of the past decade development, which is the rise of field theory, the rise of all exotic field theories. Okay, so this is the part of my motivation. And here is the outline where the motivation part is already covered, and which is a pretty long introduction, probably exotic topic deserves a long introduction. And then we will start to talk about particularly one small piece of a lot of things that I introduced, which is a bit rate bound of superluminal travel in some of the theories. And here, let me start with the K-sense theory, very simple, the most local superluminal theory that we're talking about. And here is the Lagrangian of the K-sense theory as a function of the kinetic term. And the sound speed of the K-sense, as I mentioned, is dependent on two things. The one thing is if there is a background, okay, if there is overall non-vanishing phi dot, and also dependent on the second derivative of the Lagrangian. If there is a background and the second derivative of the Lagrangian is negative, in this case, the sound speed is greater than 1, okay? And there are a lot of discussions, debates on this possibility of the sound speed greater than 1. And first of all, in terms of closed time-lag curve is not a problem, but in terms of the violation of positivity bound is indeed a problem, that the UV completion of this kind of theories cannot be at the same time local, analytical, unitary, and Lorentz invariant. So this is a very big problem or limitation of such theory with faster than light speed of light, faster than light speed of perturbations. However, it doesn't completely forbid this possibility to be discussed. For example, if we imagine some of these properties are not from the very UV theory, but if they are emergent, okay, doesn't have we don't have that in the UV theory, but emergent in IR theory, then I think we are still allowed to discuss the possibility of the sound speed faster than light. And in this particular type of theories, if you allow arbitrary background and arbitrary coupling constants, then the speed of propagation can be arbitrarily fast, depending on the background. It can be thousands, millions of times speed of light, or any possible value. Okay, and here what I'm talking about is, although in this theory the speed of the perturbation can be as fast as you want, but the transmission rate of information cannot be as fast as you want. And actually, the idea is very simple. It's very simple. Why? Because the necessary condition for the speed of light is faster, speed of perturbation is faster than 1, is there exists a non-zero second derivative of this Lagrangian, and this that there are some interactions, okay? There has to be some interactions. And to be more explicitly, if we separate phi into phi naught, background, time dependent, and fluctuations, then the second order action of the fluctuation has the term of phi naught squared dot and phi phi dot squared, fluctuation squared, which means a modified sound speed. And at the third order, there must be a term phi dot and phi dot cube. So the phi, the fluctuation cannot be large. If the fluctuation is large, the theory is nonlinear. And here I'd like to stress that this is not a particular feature of this particular model, but it is very general. It's very general in the sense of effective field theory of inflation, that as long as you have a modified sound speed in a unitary gauge and you want to restore that and consider restore the unitary gauge, and a hierarchy of interactions arises, and the third order interaction is a must. And in the community of non-Gaussianity study, this is very familiar, that once you have a modified sound speed, there will be large non-Gaussianities. In that case, sound speed is smaller than 1. But here I'm talking about the possibility of sound speed is greater than 1, okay? So what I mean is, in general, pretty generally, there is nonlinearity. And what nonlinearity means is it will constrain the value of the fluctuation. The fluctuation cannot be large. And once the fluctuation cannot be large, that means the information that you transfer cannot be large, cannot be a lot of bits, okay? And then there is a bitrate bound, and that bitrate bound, as I will show, will be a decreasing function of the sound speed, okay? If you have a larger sound speed, the speed of information is larger, but the bit rate actually decreases. So if you want low latency, so for example, if you just want to send a few bits of information, in case we have this matter, then it's very nice to use this faster than light channel. But if you want to, for example, download a movie, so you want to have a high bit rate, then it's probably more preferred to have CIS equal to 1. Then you don't have any constraints at all. So this is the take-home message of this talk. And now I'm showing you how this arises in a little bit details. Actually, the derivation is very simple. Okay, so the setup.
Sorry, can I just ask a question? This exotic method that you need that you're talking about for these theories to get superluminality, like what do you say would happens to them? So I'm assuming that you're in the context of cosmology, you want it to resolve the horizon problem stuff that inflation does, but what do you say happens to it afterwards? Because it's not something that we seem to be able to see, right?
So let me, I'm not sure if I understand your question properly, but are you saying the faster the, so appearance faster than light because of the expansion of the universe?
Yeah, and like,
right, exactly. Yeah, thank you.
And thank you. One other thing I want to ask was that, so obviously this resolves some of the issues of the universe, but would a more natural potential like alternative would be something like varying speed of light, where you have intrinsically a varying speed of light theory, like the stuff that Xiao Magejo proposed, I don't know when, like in the 90s or something, where you don't need necessarily another form of matter, and it kind of like naturally comes from the theory.
Yeah, thanks a lot. Thanks a lot for the question. So indeed, depending on how you define speed, indeed, the expansion of the universe in some sense can be considered to be superluminal, but it is one-directional superluminal. That the information just go fast in physical distance in one direction. So that doesn't allow you to either travel back and forth faster than light or send information back and forth. And I'm not very familiar with the theory of faster than light by Magejo and collaborator, etc. But in my impression, that is also homogeneous and isotropic faster than light. So that if it is the case, I'm not an expert, but if it is the case, that doesn't satisfy our need of space travel. And actually, that is why one of the reasons I'm saying that the original paper on wormhole is a very nice read, because there are a few conditions very explicitly listed that if we want faster than light travel to be useful, so what are the possible expectations? You may read that. Yeah, thank you very much for the question. Okay, so now let me come to the technical details. So in the technical detail, actually it's pretty familiar that we start from a modified kinetic term theory, and to make the effective field theory of these cases to be larger validity, we expand around a fixed background, which is made by the kinetic term of phi dot. And then, everyone in terms of working on non-Gaussianity know how to do these expansions, that we expand the Lagrangian into the second order and interactions. In terms of the second order, there are the for example, the C2 term, which modify, which is from the x squared, and that modify the speed of sound, and also that modify the interaction, generate interactions. Okay, and we will see the consequence of these interactions. The consequence is that if we require the fluctuation to be linear, okay, well, not exactly, but the linear term dominate over the nonlinear term, not completely nonlinear. In this sense, the phi dot will be required to be smaller than the background phi dot divided by CS squared. And recall that we study CS greater than 1, and that means this constraint, this requirement is more constraining than naively we expect, which is var phi dot is smaller than phi dot. Okay, I think people all know, people know this. All people studying this kind of theory all know this. And we do it, we proceed a little bit further, that first of all, this implies a constraint on energy flux. Energy flux that the second order fluctuation energy flux will be smaller than phi dot squared divided by CS5. And in some components divided by CS5 and some components divided by CS6. So this is the constraint on energy flux. And if we are limited to classical theories, this is the only thing that we can say. Yeah, before moving to semi-classical, I mean, including a lot of quantum things, let's discuss a little bit more about this classical bond, okay? So because our motivation is to think about a bit rate bond, how efficient information can be transmitted, okay? If we think about information in terms of information theory, so probably this bond is too strong to be meaningful. Why this bond is too strong to be meaningful? This bond requires at every point in space that at every point in space, the second order Lagrangian is greater than the third order Lagrangian. However, as is well known in information theory, ever since Shannon, groundbreaking paper of information theory more than half a century ago, that we know that actually if there are some loss of information, I mean practically, some noise in the information channel, some practical loss of information, still we can have reliable communication. As long as the loss is not significant, the drop of bit rate is not significant. Why I'm mentioning that is if we just have maybe a few points in space that violate the bit rate bound, that violate the energy density bound, in this case actually doesn't hurt the bit rate very much. So this local constraint on the bit rate is probably too constraining. And a little bit stronger bond is globally constraining on fluctuation modes, that we require each of the fluctuation modes is linear. And again, this is also too constraining that we can imagine that if we have a million of modes, only one mode is nonlinear, that again, only a small part of information is noisy. So it's still straightforward to, if we add some redundancies, still doesn't hurt the bit rate very much.
Sorry to interrupt you. Sorry to interrupt, but there are a couple of raised hands that I think's about what you're discussing now. So Eugene, do you want to ask the question?
Yeah, hi. This is just a simple question, right? So you say the constraint on flux is,
yes.
It seems like you're using the 0,0 term of TOO.
Thank you very much. Yes, actually here I'm writing the mu term. Actually, if we talk about the 0,0 term is similar, but there is a sound speed to the 6th power instead of 5th power.
So you're talking, it's the 0I term basically that you're calculating. That is the...
Actually, I will talk about the 0,0 term.
Okay,
yeah, I will come to that.
Oh no, my question is that when you talk about flux, right? You're trying to say, okay, there's some flux of energy, right? I would normally think that is the 0I term.
Right. Yeah, thank you. Yeah, sorry, maybe my terminology is not so good. Yeah, what I actually mean in this equation is T mu nu, and actually later what I will use is T00. Yeah, as I will show you. Yeah, thank you. Thank you. And
also Alex raised his hand. Alex, did you want to ask now or at the end?
Yeah, I think it's worth asking now. Hi, great to see you. Look, very simple question. I'm a bit puzzled. Which of the energy momentum tensors are you using there? Because
fluctuation, second order fluctuation.
Right, but think in the following way: you can write an acoustic energy momentum tensor, which is conserved with respect to the acoustic covariant derivative, and you can write a normal one. The problem is that neither of them is properly conserved, right? So the question is, which energy do you have in mind? Because you are in the background. And
by acoustic, you mean seen by the effective metric?
Right. You can write an energy momentum tensor seen by effective metric, and that's covariantly conserved. And you can write just normal quadratic whatever expansion.
Here I'm writing in the normal G mu, and not the effective metric. This is an interesting point, but in the later discussion, it's enough for me to write in terms of G mu.
The question is that it's not conserved, right?
Right. Yeah, right. But this will not be a problem in my later discussion.
Okay, great.
Yeah, thank you for the comment. Okay, so I'm here that the global constraint about each mode is linear is still too restrictive, and one more practical bound is if we consider an average mode is linear. By average mode is linear, I mean that if we have a probability distribution of modes, I will make it more precise, a probability distribution of modes and the energy of modes and integrate over the measure of modes. And then this quantity satisfying is the second order is smaller than, is greater than the third order. So this is, I think, more reasonable from arguments of information theory that this means a large amount of information will be noisy in the channel. So the bit rate will drop significantly. Actually, I don't have a mathematical proof, but I think this argument motivates us to be more interested in this average and globally, I mean the AGC, average and globally constraint. All right, and then actually I don't have a lot of time, but actually the remaining part is very simple, okay? The remaining part, we will add quantum mechanics. And once we add quantum mechanics, we know that if we don't add quantum mechanics, then we can have arbitrary amount of information transmission given energy. But once we add quantum mechanics, we know that each wavelength, the energy is bounded by a quanta. So we are not going to have arbitrary amount of information. So that is bounded by quantum mechanics. Okay, and the setup in equations that we this is what we do, that we study semi-classical signaling. By semi-classical, I mean the signal is still described by some coherent states. And actually, by coherent states, if we are close to the bit rate bound saturation, then actually every state is pretty close to a quantum state. But nevertheless, to be general, we start from coherent states, but it's not completely general. For example, here, I'm not considering so two places sharing EPR pairs and fully quantum information. So I'm not there yet, although I'm interested to study it in the future. I study semi-classical signaling, and we calculate the Shannon entropy. And this is the Shannon entropy, which is the probability and the logarithm of probability integrated over the mode functions, where this mode functions has the normalization conditions, where integration of the mode function, integration of the measure and the probability will give you 1, and the energy, the expected energy also can be calculated. And here I divide the y and z direction, where we have IR cutoffs. We consider a section, either a box or fiber, etc., to transmit information. And this energy can be calculated. And also, as we just discussed, we have the average global constraint, which is the average energy is smaller than the maximum energy. Okay, so this is the mathematical setup of the problem. And actually, by this mathematical setup, it immediately make the problem solvable, transmit the problem into a familiar problem, which is in statistical mechanics. How do we calculate entropy of a, for example, photon gas? Okay, so the mathematical structure is the same in the sense that we have a constraint, which is probability normalized to 1. And also we have a constraint on energy. So this is less or equal, but it's intuitive to imagine that when the bitrate bound is saturated, here we should take the equal sign, because otherwise we can add more moles to transmit information. So this equals to the maximum, and we have two constraints. With these two constraints, we extremolize this quantity, and that means actually extremolize the entropy, the Shannon information, which is similar to entropy equation. Extremolize the Shannon information given these constraints. Okay, and the solution is again familiar, which is the extremalized probability takes the form of exponential, and also the extremalized Shannon information takes the form of a little bit complicated, but still a pretty compact form, where this gamma is the solution of this equation. And this entropy bound that we consider a cross-section of information to be transmitted. For example, from the Earth to Alpha Centauri, there is a length. Okay, the information contained in this box can be directly translated into a bitrate bound, because we know the sound speed and we know the length of the box. Okay, and this is the bitrate bound. And actually, that relates to Eugene's question that I am discussing the energy density, but that's up to a speed of sound, up to a CS related to the T0i. And actually, if I divide the T0i, divide the speed of sound to here, actually, I think I can equally formulate in terms of energy flux. But simply, I didn't do the calculation in that way. And by the way, we can also write a dimensionless bitrate bound, dimensionless bitrate bound in the var by just factorize the dimension. And for example, this is the dependence of the bitrate as a function of the sound speed and as a function of phi dot. Okay, in this figure, you can see clearly that this yellow color corresponds to a larger bitrate, and this blue color corresponds to smaller bitrate. So given a fixed background, fixed phi dot, then the larger sound speed is, you will have a smaller bitrate. So the bitrate, this R star, is a decreasing function of sound speed. And we can also see it clearly from different limits. Here I read a dashed line that we can subdivide into two regions, the so-called high temperature regime and the low temperature regime. The so-called high temperature regime corresponds to the limit where the number of moles are bounded by the effective field theory cutoff. And the low temperature regime, the information carried by moles is bounded by the Boltzmann factor. Okay, in these two regimes, we can solve the factor of gamma explicitly, and we can show the bitrate bound in the low temperature limit is scale size sound speed, something like some inverse power laws. And in the high temperature regime, the scaling of bitrate is something logarithm, but still is a decreasing function of the sound speed. All right. So this is what I'm going to, what I'd like to talk about. And here is the conclusion. Conclusion take-home message, very simple, that superluminal means nonlinearity, at least in effective field theory of inflation, this class of Lagrangians. And then this nonlinearity means that there is an energy density bound. And energy density bound plus quantization will give you a bitrate bound. And so this current work, so although we have illustrated this idea, but there are a lot of things that we need to further work on. For example, we need Lorentz violating background. And that Lorentz violating background has a lot of constraints from standard model interactions, especially if we think it a little bit more realistic that future civilization want to make this kind of faster than light travel, then we need to couple it to a standard model sector. So what are the constraints? And also, what about higher dimension operators in effective field theory? This we have some preliminary results that the bound is very similar. And also, is there more mathematical proof that our AGC, average global constraint, is justified? And also, what about other superluminal mechanisms? For example, superluminal from extra dimensions. If we naively consider the effective field theory of these extra dimension theories, that will probably reduce to the PX theory. Yeah, I don't know, just naively. And in that case, probably also related to what we are discussing, but it's also interesting to see what happens in the UV, a little bit UV theory, that as we go to the extra dimension, there is a blue shift factor, and maybe that can break the effective field theory more easily, which I don't know, just some hand-waving arguments. And also it's interesting to go to fully quantum descriptions. And that's it, thank you.
Okay, Yi, thanks a lot for a very nice talk. So I can see 2 hands raised again. So Eugene, want to go ahead?
Yeah, I think Vikman raised his hand first, but I'm happy to go second if you like.
Yeah, I didn't know to do it first, but choose between yourselves.
Okay, I'll go first then. So I'm slightly, maybe it's just my misunderstanding of what you're trying to say, right? So if you can go back to the slide where you calculate that you maximize the Shannon entropy. So if I understand it, your P stands for the probability of finding each coherent state Z, right? That is what your P stands for. And then what you do is that, okay, I have a restriction on my possible phase space, but with the AGC bit bound, that is my restriction on my possible phase space.
Right.
And then you say, okay, now I'm going to maximize my entropy, my Shannon entropy of this phase space. So what are the configuration that give me the maximum maximum entropy?
Exactly.
And then you use that as your communication channel, if you like. You say, okay, well, that's the maximum entropy, so I have a lot of possible configurations, and that is information I can encode.
Yeah.
But that seems to, sure, I mean, yeah, you can, the fact that you have enough space to encode information doesn't mean that you can encode those information, right? So you still need to come up with a mechanism of saying, how do I use this entropy? In fact, when you wrote that, I immediately thought, okay, well, you are in the equilibrium state, right? That's the maximum entropy state, is the equilibrium state. So in other words, the information you can transmit is 1, basically the temperature of your state, and that's it, because it's the maximum entropy state. So maybe I'm misunderstanding what you're trying to do here, but is there a quick way to reconcile that? Because
that depends. So I'd like to have 2 comments. The one comment is that depends on if you talk about the cross-grained or fine-grained entropy states. That if you know all the detailed configurations, still you can calculate the thermodynamical entropy. Yeah, but still, if you know all the configuration, it makes sense that this state can carry information. This is the number 1 thing I'd like to say. And the number 2 thing I'd like to say is, by equilibrium, if it's not coincidental, also evolve interactions. And here exactly is related that I restrict the interaction to be under control. So it's not really going to be the equilibrium that we have no information to be transmitted.
I see. So you're encoding information in the microstates, basically.
Yes, exactly.
I see. Okay.
Yeah, thank you.
I have kind of mixture. First, I would like to comment that the only conjectured way to UV complete such theories is what Guy proposed as classicalization. And that's actually very interesting, how to reconcile this information transfer with such a way of basically unitarizing things. But that's kind of side comment, even though it's probably crucial for further UV studies. But what I don't really properly understand is that is there a maximum bit rate in all this series if you vary the speed of light and your cutoff? Is there any maximum you can reach, like universal bound or something?
By maximum, because it's a decreasing function, or as a function of speed of light. So if the speed of light is approaching infinity, the bit rate is approaching 0.
Mm-hmm.
Yeah,
But
that actually means the theory is highly nonlinear. Even a 1 bit transformation can make the theory nonlinear and non-perturbative.
Sure, but does this formula only applicable for asymptotically for very large speed of sound, right? Really, speed of sound much larger than 1.
No, this formalism applies for any speed of sound greater than 1. By greater than 1, I mean if it's equal to 1, it's perfectly okay with that linear theory. Or smaller than 1, so it's another story. Okay, so for any greater than 1, but if we have explicit closed form expression, these are the constraints. So so sound speed and the phi dot, which is larger.
Mm-hmm. Mm-hmm. Okay. Well, thanks. I think I will write you more comments.
Thank you.
Very interesting. Thanks a lot.
Yeah, just to remind you, there's also the Slack channel where you can continue the discussion. Okay, so thanks a lot, Yi, for a nice talk. Now we're